Spectroscopy 1, Introduction to Analytical Techniques, Index of Hydrogen Deficiency and Infrared Spectroscopy. The essential idea here is that analytical techniques can be used to determine the structure of a compound, to analyse the composition of a substance, or to determine the purity of a compound. Spectroscopic techniques are used in the structural identification of organic and inorganic compounds. The nature of science: improvements in instrumentation. Mass spectroscopy, proton nuclear magnetic resonance, and infrared spectroscopy have made identification and structural determination of compounds routine. Also, models are developed to explain certain phenomena that may not be observable. For example, spectra are based on the bond vibration model. So, analytical techniques. There's three main types, and up here you can see we've got miscellaneous white powder. If we analyse this, we could do qualitative analysis. This would detect only the presence of a chemical in a sample, so you'd know if it contained a particular type of chemical, for example cocaine. Quantitative analysis: this detects the quantity of a particular chemical in a sample, how much of that chemical is in there, and you could be by percent. And finally, structural analysis can be used to find the arrangement of atoms in a molecule. And there's chemical techniques such as empirical formula determination through IHD, which we'll get to later, and spectroscopic techniques such as IR and NMR, infrared spectroscopy and nuclear magnetic resonance. A variety of techniques to determine the structure and identity of unknown compounds. Let's look at these techniques. We've got infrared spectroscopy, which uses obviously infrared light to study molecules and compounds. Mass spectroscopy, which uses the mass of substances to determine what they are comprised of. We've got NMR spectroscopy, which is nuclear magnetic resonance spectroscopy. We can use percent composition and empirical formula to work out the structure of substances, and the index of hydrogen deficiency too. Each technique tells us something different about the compound. Chemists use a combination of these techniques when they determine the structure of an unknown compound. The index of hydrogen deficiency, or IHD, is a measurement of the degree of unsaturation of a compound. Saturated compounds contain no double bonds or triple bonds in their carbon chains. They only have single bonds in the carbon chains. Unsaturated compounds have double or triple bonds in the carbon chains. The IHD number is equivalent just to the number of hydrogen molecules needed to convert an unsaturated molecule to its corresponding non-cyclic saturated equivalent. So if we want to turn but1ene into butane, we would need to add 2 hydrogen atoms, C4H8, to make C4H10, and so that would be 1 hydrogen molecule. So it would have an IHD of 1. Butane, C4H6 to C4H10, we've got 6 hydrogens going to 8 to 10 hydrogens, and so we'd need 4 hydrogen atoms or 2 hydrogen molecules. So an IHD of 2, cyclobutane, 8 to 10, 1 hydrogen molecule, so IHD of 1, and buta-1,3-diene, you've got C4H6 going to C4H10, so we're going to need 2 hydrogen molecules, which gives us an IHD of 2. So let's have a look at index of hydrogen deficiency from structures. This table shows the index of hydrogen deficiency value for unsaturated elements in a compound. Adding up the IHD values for the elements present in a compound gives the overall IHD for the compound. So double bonds give us 1, triple bonds 2, a ring structure that is non-aromatic gives us 1, and a benzene ring or an aromatic ring gives us 4. So if we look at limonene here, you can see it's got 1 double bond, it's got another double bond, so 2 double bonds and 1 ring structure. Okay, so 2 double bonds plus 1 ring is 1, plus 1 plus 1 gives us 3. So it would have an IHD value of 3. Have a go at the IHD for these structures. Press pause and go through them. Okay, so methylbenzene, you've got a benzene ring and a methyl group, so you've got 4 from the benzene ring. Linolenic acid, got 1, 2, 3 double bonds, and also this one over here, so it gives us 4. Cyclohexane, it's got just the cyclic structure, but it's not aromatic, so that's an IHD of 1. Cyclopentadiene, so it's got a cyclo, which is 1, diene, so 2 double bonds, so it's going to be 3. Yep. Aspirin, it's got your benzene, which is 4, double bond here, 5, double bond here, 6. Yeah. And propionyl benzene. So we've got our benzene here, which is 4. We've got the triple bond here, which is 2. 4 plus 2 is 6. It gets a little bit more complicated than that, but there is a generic formula for an organic compound, and you can see here it's a bit long-winded. Little c stands for how many carbons, H how many hydrogens, N for nitrogens, O for oxygen, which doesn't really matter, and X for halides. And this is the formula we would use. IHD equals 0.5 multiplied by 2c, the number of carbons, plus 2, minus the number of hydrogens, minus the number of halides, plus the number of nitrogens. So let's have a go at that for cocaine. 17 times 2 is 34. Then let's add 2, 36. Then take away the number of hydrogens. It's got 21, so 36 minus 21 is 15. 15 plus the nitrogens. There's 1 nitrogen, so 16. And then we've got to divide it by 2 or multiply by 0.5, which is going to give us 8. Cholesterol, we've got 27 carbons. Multiply that by 2, you get 54. 54 plus 2, 56. Minus the hydrogens gives us 10. And then we don't do anything with oxygen, so 10 times 0.5 is 5. Haha, my math is working. And aniline is a dye. It's C6H7N, and we've got 6 times 2 is 12, plus 2 is 14, minus the 7, back down to 7, plus 1, 8, times 0.5 is 4. And if you wanted to draw a structure for aniline that is consistent with IHD, and it's a 4, and you can see it's C6H7, it's probably going to have, oh, let me get you something better than that. 1 minute. It's obviously going to have a benzene ring in it for the 4, and then you just want to stick, what do you want to stick on there? We want to put NH2, so I have an NH2, and the 4 comes from the benzene ring. Look at IHD for molecular formulas. To determine IHD for compounds with a molecular formula, we're going to determine C4H8O2. So let's use the math first to find out IHD. 0.5 times 2 times 4 for the carbon, plus 2, and minus 8 for the hydrogens. We don't need to bother with the oxygen, no halides. So we've got 1. So if we're going to suggest structural formulas for 3 isomers of this, that are consistent with the IHD value, we're going to need to think of something which has 1 double bond, or a ring structure would be a sensible approach. Obviously the carboxylic acid would be an obvious one because we've got the 2 oxygens there. You'd have an ester, or we can just move that ester group around as well. The 3 possible positions, all would be fine. We're going to have another carboxylic acid group, but have some branching going on there, and we could also have a cyclic group, and this has an intentional mistake, as you can probably see. We just get rid of that there, and then we're just going to stick an oxygen. That's better. And the cyclic ring structure gives us 1 there. Let's think back to the electromagnetic spectrum. Remember, you've got frequency and energy increasing as you go from radio waves through microwaves, infrared, UV, X-rays up to gamma rays, and you've got the wavelength increasing the opposite way as we go from gamma rays through X-rays through to the radio waves. So energy and frequency are directly related. Frequency and wavelength are inversely proportional. And remember, you've got to know this, okay, and you certainly have to know this visible spectrum, 400 to 700 nanometers, okay. Molecules or atoms can absorb different forms of electromagnetic radiation. Different forms of electromagnetic radiation interact with atoms in different ways, and they're used in different analytical techniques. So let's look at gamma rays first. And just remember there that energy is decreasing as we go from gamma rays to radio waves. The effect on chemicals. The gamma rays interacts with the nucleus. However, we don't use gamma rays in analysis ever since the Hulk was created during a catastrophic accident in an experiment. X-rays, these interact with the inner electrons, and we use these for crystal lattice structures in X-ray crystallography. UV and visible light, these interact with the valence electrons, with those outer electrons, and the electron transitions between energy levels. Infrared light, this affects the vibration of molecules and the type of chemical bonds. It's different for different types of chemical bonds, so bonds vibrate differently, and infrared light interacts with that vibration. Okay, it affects the vibration of the molecules. Microwaves, they affect the rotation of molecules, and you can calculate bond lengths from that. And finally, radio waves, it affects the spin of nuclei. Okay, we'll describe that later on. And it tells us information about the environment around atoms in a molecule, and it's used in nuclear magnetic resonance spectroscopy. Okay, let's think back to some formula that we know and love. We've got speed of light equals frequency multiplied by wavelength. We know that energy is Planck's constant multiplied by frequency, and we can put these two together to form this fantastic formula, which is energy equals Planck constant multiplied by the speed of light divided by the wavelength. Okay, and these are given in table 1, the constants table 2. Principles of spectroscopy. Wave number. Wave number is a common unit used in spectroscopy, and it's just the reciprocal of wavelength, so it's units centimeters to the -1, or 1/centimeters. To calculate the wave number for ultraviolet radiation with a wavelength of 2 × 10⁻⁷ meters, we would first of all convert wavelength into centimeters, so we'd use conversion factors or dimension analysis. So we've got this in meters. Our conversion factor would be there are 100 centimeters for every 1 meter. Make sure that the thing you want to cancel out is on the bottom. Meters and meters will cancel, giving us centimeters. We'll get 2 × 10⁻⁵ centimeters. Next, we need to convert that to wave number, and it's just a reciprocal. So we'll just put the answer underneath 1, do the math, and you get your answer in centimeters to the -1. Okay, some more calculations. Carbon dioxide molecules absorb infrared radiation with a wavelength of 6 × 10⁻⁶ meters. We're going to calculate the energy absorbed per mole. Okay, so step 1, we're going to find per molecule. We'll use the two constants, which we can plug in, and we've been given the wavelength, so put that in 2. So we know the energy per molecule. Next step, we're going to use conversion factors. Fantastic conversion factors here. We know that 6.02 × 10⁻23 molecules is 1 mole, and so we know what it is per molecule. We do the math to give us the answer in joules. Example 2. A molecule absorbs infrared radiation with a frequency of 3 times 10 to the 13 seconds to the minus 1, or hertz. Calculate the wavelength in meters and the wave number. First of all, use the formula. We've got the speed of light divided by frequency. Speed of light is 3 times 10 to the 8. And I know the frequency is 3 times 10 to the 13 hertz to give us the answer in meters. Next, we convert meters to centimeters, and we can use the conversion factor here. 100 centimeters is 1 meter. Do the maths to get the answer in centimeters, and then we use the reciprocal to find the wave number. The absorption of infrared radiation. You can see here that the bond is drawn a little bit like a spring, and it is a bit like a spring. They're constantly bouncing. These two atoms are moving towards each other and away from each other as they vibrate. Different chemical bonds and molecules vibrate at different frequencies and only absorb radiation with a corresponding frequency or wave number. The radiation absorbed by vibrating chemical bonds is in the infrared region of the electromagnetic spectrum. So you can think of a red disco ball and two atoms vibrating as they dance under the red light. Why is the absorption of infrared radiation by molecules important, you ask? Well, it helps in identification of molecules, and it also is responsible for the greenhouse effect. Absorption of infrared radiation. Only polar bonds absorb infrared radiation. So infrared absorption only happens when a bond vibration produces a change in dipole moment. Okay? So nitrogen and oxygen, they aren't greenhouse gases. They only have non-polar bonds, so they can't absorb infrared radiation. Conversely, carbon dioxide and methane, which are greenhouse gases, have polar bonds, so are able to absorb infrared radiation. This non-polar bond and a polar bond interact with infrared differently. No bond dipole at any length, no matter how far they're stretched or squished together, it wouldn't be polar, and so it's inactive with regards to infrared radiation. However, a change in this bond length will change the strength of the dipole bond, so it is active with regards to infrared radiation. Vibrations in polyatomic molecules. Bond stretching or bending must change the dipole moment of the molecule in order for infrared absorption. And there's different kinds. You can have a stretch, symmetric stretch, asymmetric stretch, and symmetric bends. Okay, let's have a look at a few of these. Before that, note that these arrows aren't representing bond dipole strength. I know we're used to seeing arrows doing that. In this case, the arrows are representing change in bond length and angle. So, a symmetric stretch with water, these hydrogen atoms are moving away from the oxygen, and obviously they have different electronegativities, so it's IR active because it's going to be polar. The asymmetric stretch here, again, you've got it's non-symmetrical, and you've got movements of a polar bond, so it's this asymmetric stretch is in fact infrared active. The symmetric bend here, you can see non-symmetrical, and you've got a polar bond stretching, so it's infrared active. Let's look at this one here, the asymmetric stretch for carbon dioxide. You can see that because this one's squished, this one's length, this one's stretched, there's going to be an overall dipole change on the molecule. Okay, so it's going to be active. This one here, if the oxygens are moving away from the carbon evenly, they'll cancel each other out, so it won't be active. But this one here, again, this bend where the oxygens are bending down is causing the molecule to be non-symmetrical, and so you've got a polar molecule. It's going to be IR active. Here's a table of infrared absorption where certain bonds absorb infrared light, which wave number of infrared light is absorbed. You can see carbon iodine bonds 490 to 620 and the intensity is strong. Let's have another look. Oops, let me just get rid of that. There we go. Carbon double bond oxygen in aldehydes, ketones, carboxylic acids, esters. You've got a very strong and sharp peak at 1700 to 1750. Another very common one is in alcohols, the hydrogen bonding in alcohols goes a nice big strong broad peak between 3200 and 3600, and there's several others, as you can see. So a molecule absorbs infrared at a wave number of 1720. Which functional groups could account for this absorption? Let's go back and have a look. 1720, it could be a carbon double bond oxygen. Which one of these has a carbon double bond? Well, we know what aldehydes do, and we know esters do, we know the ethers don't. So we're looking at 1 and 2. Aha, and we're correct. A molecule has the molecular formula C2860. Its infrared spectrum shows an absorption band at 1000 to 1300, but no absorption above 3000. Deduce its structure. Well, let's consider some isomers first. Could be ethanol, could be dimethyl ether, couldn't it? These are two possible things it could be. We've considered the IR data. We've got 1300 absorption, which equals a carbon oxygen bond present in both structures. Yep, and there is a carbon oxygen in both structures. However, if it was ethanol, there should be a large signal at 3200 to 3600 due to the OH bonds in the alcohol, and it's absent. So the structure must be that of dimethyl ether. Identifying the infrared spectra. So you can see you've got transmittance over here, and you've got your wave number over here. Let's look at the infrared spectrum of ethanol. The lower the percent transmission of it's the greater the absorbance of infrared radiation. So this peak here is where it's being absorbed. Okay, so it's getting lower in transmittance but greater in absorbance. Okay, that makes sense. Another thing you want to notice is the x-axis scale is not always linear. Okay, you've got a gap of 1000 there. As you go further down, it's a gap of 500. Okay, so if we recall, a great big broad peak here is due to the characteristic of hydrogen bonded OH bonds in alcohols. We've got this peak here just below 3000, 2900, and this is due to CH bonds, and we've certainly got some CH bonds there. And we've got this bond here. One of these two signals, you can see these two peaks, could be due to the CO bond, this carbon oxygen bond, but in this region here it's difficult to be 100% certain because this is called the fingerprint region, and interpretations in this region could be quite difficult. Let's have a look at another one. Ethanoic acid. We've got the broad signal of 3000, which is characteristic for the OH bonds in carboxylic acids. We've got this very strong singular peak here at 1700, characteristic of the carbon double bond oxygen. And again, we've got this little peak here, which could be a carbon oxygen bond, but it's in a fingerprint region, so we can't be 100% sure. Okay, example 3. You're going to do this one. A substance with the molecular formula C4H8O2 produces this infrared spectrum. Can you identify the class to which this molecule belongs and suggest possible structures? Press pause and have a go. Okay, so the class is probably an ester, and you can have several possible structures. We've got this strong CH group here. We've got a nice strong carbon, double bond oxygen here, and obviously we can't really use the fingerprint region. So what is this fingerprint region all about? Well, it occurs between 400 and 1400 centimeters to -1. It's usually really complex spectral pattern, and it's unique for different compounds in the same way the fingerprints are unique, and I suspect that's why they call it the fingerprint region. It ain't unique for enantiomers. It can be used to identify unknown compounds by comparison with a library of known compounds. However, this isn't the main use for it. The main use for infrared spectra is to confirm the presence of particular groups, these functional groups. It can be used for detecting ethanol in breath tests. Let's look at the fingerprint region for proben 1-ol and proben 2-ol. You can see that these two have the same spectral patterns outside the fingerprint region, very similar. You've got this big broad peak, you've got the peak just below 3000, and you've got these peaks just below 1500. But then in the fingerprint region, they're very different. So therefore, this region of the infrared spectrum can't distinguish between the two isomers other than other data is needed. Proben 1-ol and proben 2-ol have different and unique patterns in the fingerprint region, so you could use these patterns to identify. You should take a look at the spectral database for organic compounds here for your own amusement. Oops. Splendid. Goodbye.